Thank you. Good morning. So I'll start, as is customary, by thanking the organizers. It's customary, but sincere thanks. It's a great pleasure to be here. So the work I'm going to present this morning is based on a joint paper with Charles and with Marc that is on the archive and that was presented at the Fox conference in this fall. I won't repeat the title, but here is the outline for this talk. I will first set the scene by reminding you what Ramanujan graphs are and what non-backtracking matrices of graphs are. Then I'll also introduce the stochastic block model, which is the random graph model that we will be considering in this talk. And I'll tell you a bit about community detection in that context. Then finally, I'll give you the main result that I want to tell you about, which is some characterization of the non-backtracking spectrum of random graphs as drawn according to the stochastic block model. And this has two interesting consequences, this result that I want to tell you about. The first one is a proof of the so-called spectral redemption conjecture that has been done by physicists and mathematicians and computer scientists who were looking at community detection in the context of stochastic block models. And also another interesting consequence of the main result is that we can claim, because of this result, that Erdos-Renyi random graphs, which are irregular graphs, enjoy with high probability a Ramanujan-like property, which extends the basic Ramanujan notion known for regular graphs. Okay, so let's get started. So first, Ramanujan graphs. I suppose most of you are very familiar with the notion, which was introduced in the 80s by Lubotsky, Phillips, and Sarnak. So that applies to regular graphs. So if S is the common degree of nodes in a regular graph, a graph will be said to be a Ramanujan if all the eigenvalues of its adjacency matrix whose modulus is strictly less than S, which is the spectral radius of the adjacency matrix, are less than or equal to twice square root of S minus 1. So that's the definition. And to put it in context, it's useful to remind the theorem by Allen and Bopana in 91, which says that it is actually the best spectral separation you can hope for a regular graph, in the sense that any S regular graph will be such that its second largest modulus for its eigenvalues will be at least twice square root of S minus 1, which is the term appearing in the definition of a Ramanujan graph, minus some correction term, which will go to 0, at least as 1 over the diameter of the graph. So that is, in a sense, telling you that if you fix the degree S and you let the number of nodes go to infinity, then the diameter has to explode. And so this correction term has to go to 0. Hence, the spectral separation can asymptotically not be smaller than this, the one you have in the definition of a Ramanujan graph. To put it into a broader context still, it's useful to remind you of the theorem of Friedman, who is in the room, who proved in 2008 that random regular graphs with a common node degree S larger than or equal to 3 are such that the second largest modulus of the eigenvalues of the adjacency matrix are precisely twice square root of S minus 1 plus little o of 1 with high probability. Hence, they are quasi-Ramanujan, the quasi coming from the slight correction that vanishes as the number of nodes goes to infinity. So as a warm-up, I thought I would sketch some of the argument that goes in the proof of the Allen-Bopana theorem. So I'm sure many of you have seen some proofs of that, but there is one that I came across recently in a paper by Bojan Mohar in 2010. So it's on archive. This is the title of the paper. And he provides a strengthening with an argument that I find quite nice. So I'll sketch that just now. So it's a strengthening in several respects. First, the correction term is slightly better in the version given by Mohar. So he establishes that the second largest eigenvalue of the adjacency matrix of an S-regular graph is at least twice square root of S minus 1 times a term that is going to be 1 minus O of 1 over R squared, where R should be thought of as related to the diameter of the graph. So it's you square the diameter here as compared to the original statement of Allen and Bopana, but I guess, okay, let me proceed with the argument. So the assumption is that your diameter is at least twice R plus 1 for some R. So this goes as follows. You pick two nodes U and V in your graph that are, according to the graph distance, apart by at least twice R plus 1. So you can draw a ball of radius R around each of them. And then you can consider the induced graph, which is the ball of radius R around U. You can consider the ball of radius R around V. And now, if you consider the spectral radius of this graph, this is a standard thing that it will be, because the graph is S-regular, this will be at least the spectral radius of a regular graph, a regular tree, sorry, with a common degree S and depth, so starting from a root, depth R. So you have one root, you have same number of neighbors, and then you go down to depth R. And this is evaluated. You have lower bounds for that. This will precisely correspond to the lower bound we have here. So this we can lower bound easily and obtain this nice formula, twice square root of S minus 1 times cos of pi over R plus 2. And now, once you have this lower bound on the spectral radius of this neighborhood of a node in the graph, then you can look at A tilde, which is the adjacency matrix of the union of these two neighborhoods. And you know that each of the neighborhoods, being disjoint, will induce an eigenvalue here that will be at least the spectral radius corresponding to each of the neighborhoods. So you have that lambda tilde, I'll call it lambda tilde 2 of lambda, okay, lambda 2 of A tilde will be at least, again, this thing. And once you know that, you have a very nice general thing, which is the Cauchy interlacing theorem, which allows you to relate the eigenvalues of a matrix, here the matrix A, which is the adjacency matrix of your original graph, to the eigenvalues of a matrix A tilde obtained by projecting the original matrix. And it turns out that when you restrict your original graph to the two neighborhoods, this is exactly the same as projecting onto the space spanned by the nodes in the two neighborhoods. And so you can now invoke Cauchy's interlacing theorem, and what you get is that the highest eigenvalue of the A tilde matrix is a lower bound to the highest eigenvalue of the A matrix. So you get at once that the second largest eigenvalue of A is at least this. So I find this, that's the fastest argument to the Allen-Bopana theorem I know of. And the nice thing is that it extends to not just the second eigenvalue, but to the kth eigenvalue. As long as you can find k disjoint neighborhoods of radius r in your graph, you are able to say that the kth eigenvalue of A is again lower bounded by this. So this is in that sense that it also says something about Serre's extension of the Allen-Bopana theorem. So that was a warm-up to get you into Ramanujan graphs. So, but this is the classical Allen-Bopana theorem that it is telling about. So let's move now to non-backtracking matrices. Given a graph G, the non-backtracking matrix is defined on the set of oriented edges. So for any edge in the graph, say UV, we create two oriented edges, UV and VU. And so the non-backtracking matrix B defined on this set of oriented edges is just the matrix that will have zeros everywhere, except when you consider B indexed by two edges, one feeding into the other, and without a backtrack of the second one onto the first. So I hope that is clear. So we have here first index of the entry of the B matrix is UV, and if we want this to be non-zero, the second index must be some Vy with Y distinct from U. Okay, so that's just the definition. It's a matrix that has this obvious property that when you raise it to some power k and you read the EF entry of the matrix, then this will give you the number of non-backtracking paths starting at edge E, ending at edge F, and with length k plus 1 edges. So that's fairly easy to see. Something slightly less easy to see is the fact that there is a correspondence between the spectrum of this matrix and the spectrum of the adjacency matrix. And this correspondence is embodied by this Ihara-Bass formula, which was proven by Ihara in '66. The proof was then simplified by Bass later on. So basically, if you look at the determinant of the identity minus U times this non-backtracking matrix B up to some correcting term which vanishes only for U equals 1 or minus 1, then you get another determinant which involves A this time and which is quadratic in U. And so if you massage that, you can at once see that the eigenvalues, so at least in the S regular case, the eigenvalues of B, they must be either minus 1, 0, 1, or lambda plus or minus square root of lambda square minus 4 S minus 1 over 2 for lambda in the spectrum of A. So if you know the spectrum of A, you know the spectrum of B, that is to say. And because of this remark, it turns out that you can express the Ramanujan property that was defined in terms of the eigenvalues of A in terms of the spectrum of B. And the exact way to do that is to say the following. The graph, being S regular, will be Ramanujan if the eigenvalues of B are such that you always have the Perron-Frobenius eigenvalue, which is positive and real. So that's lambda 1. And so the graph will be Ramanujan if all the eigenvalues of modulus strictly less than lambda 1 will be actually of modulus less than or equal to the square root of lambda 1. And that's equivalent to the Ramanujan property. And this can be established just by this correspondence of the eigenvalues. But the nice thing is that this definition here does not rely on the fact that we have a regular graph. So we can now say that this is a candidate for extending the notion of Ramanujan graphs to non-regular graphs. And actually, this precise property has been coined by Audrey Terrace in a series of papers. She calls it the graph theory Riemann hypothesis. So graph satisfying this, I'd like to call it a Ramanujan graph according to this extended definition, but Audrey Terrace calls it a graph satisfying the graph theory Riemann hypothesis. So there are very nice papers by her and co-authors on these notions of zeta functions of graphs, but I won't go into that. Okay, so much for the introduction on non-backtracking matrices and Ramanujan graphs. So let me now present the random graph models we'll be living with throughout the talk. So these will be the stochastic block models, also known as the planted partition models. And in fact, this is just an Erdos-Renyi graph with multiple types. So to define it, I need to introduce some number of types. So this will be fixed throughout. I will assume I have R types that nodes can have. And the nodes will then be partitioned according to their types. And so R is fixed. So that's the number of types or categories. For each category sigma, I assume I have a fixed fraction of the nodes participating to this category, alpha sigma. And then, as I said, this model is just a multi-type version of the Erdos-Renyi model. Now I will attach two nodes U and V with a probability that depends on their types only. So the precise definition is that the probability will be B sigma U sigma V for some matrix B divided by N. And here, n is going to go to infinity, but all the other things are going to stay fixed. The number of categories, the fraction of nodes per category, and the B matrix. These are the fixed parameters of my stochastic block model. And so the game then in community detection is given the graph, so you observe the adjacency matrix of the graph, can you retrieve the underlying planted partition into communities or types or categories? So here is a way to view the observation, the adjacency matrix. This is the block matrix corresponding to the expectation of this adjacency matrix, plus a noise matrix, which is thus the adjacency minus its expectation. So as I said, the game in community detection is to retrieve the blocks from the noisy matrix observation. And more precisely, you can define how successful you are in retrieving these blocks by counting how many nodes you categorized as they should be. So this is a precise definition here. So I'm using a terminology that's been introduced by physicists for this. They call it the overlap. So the first term is just counting how many nodes I categorized adequately. So sigma hat would be my estimator. The types themselves don't carry any meaning, so I can permute them around. This does not entail anything. So pi would be a permutation of the labels I assign to types. So the first sum here is counting how many nodes I labeled correctly. And then I remove some offset, which would be the size of the largest group relative to the total amount. So another way to see this thing is to view it as some kind of correlation between the estimated types and the true types. And perhaps the simplest case is when you have only two communities, so in that case, when you have just two communities, you can take the types to be +1 or -1, and then if you forget about the pi thing, the overlap would then be 1 over n, sum from u equals 1 to n of 1 sigma hat u equals sigma u minus 1/2. Okay, I'm also assuming alpha minus 1 equals alpha plus 1 equals 1/2. So that's the simplest case that is non-trivial. We have two groups of equal sizes. And you can rewrite this as 1 over n, sum from u equals 1 to n of sigma hat u, sigma u, minus 1 over 2 minus, sorry, so if these are, okay, if these are same sign, then I get a 2 and this gives me a 1. If these are opposite signs, this gives me a 0. So that is indeed the same. And so if you write it this way, you can see that this is 1 over 2n times sum from u equals 1 to n of sigma hat u, sigma u. So this is really the empirical correlation apart from the factor 1/2 of the true spin vector of signs +1 and -1 with the estimated spin vector. Right, so the game is to achieve a high correlation or a high overlap. Achieving 0 overlap is always a possibility. You can assign to each node the type corresponding to the largest community. And this will give you a first sum that is precisely the maximum of the alpha sigma. And so this 0 overlap is easy, 0 correlation is easy. The game is to achieve positive overlap or correlation. So let me give a bit more background on this problem. In the specific two community case with symmetric parameters, so I have two communities, equal sizes, each one taking half of the nodes, and also symmetric parameters. So I have fully specified my model now with only two scalars. A determines the probability of an edge internal to a community. That would be A over n for two nodes in the same community. And B would determine the probability of an edge across two communities. So that would be probability B over n. So I have these two parameters, A and B. And clearly, if A and B are too close, this makes things hard. If they are well apart, life is easier. And Dessel et al. Conjectured a nice phase transition happening when you vary A and B for achieving positive overlap. So they conjectured, now it's no longer a conjecture, it's proven now, but let me tell you about it. So they conjectured that when this function tau of A and B is less than 1, then no matter what you do, any estimation procedure sigma hat will asymptotically get 0 overlap, 0 correlation. So you will not get anything from the hidden structure. There's no information in the observed adjacency matrix, so you're doomed, basically, if this parameter tau is less than 1. And this has been proven by Mossel, Niemann, and Sly a year after it was formulated. In that paper, Dessel et al. Also conjectured another behavior when tau is above this transition point. They said that positive correlation can be achieved if tau is above 1. And they conjectured it can be achieved using a belief propagation kind of algorithm. And so we had two proofs of that in 2013, one that I did myself and another one by Mossel, Niemann, and Sly. Both are in a sense not as satisfactory as the original conjecture, which said belief propagation is going to succeed because the algorithms are not as nice. And but the same year, again, So I think they removed Dessel from the author set. So Xhaka, Lamour, Mossel, Niemann, Sly, Zdeborova, and Zhang formulated in a very nice paper another conjecture concerning this very same problem. They said when this parameter tau is larger than 1, you can achieve positively correlated community detection using a spectral method based on the non-backtracking matrix of the graph. So, and that was the spectral redemption conjecture. Why is it a redemption? Because standard spectral methods based on the raw adjacency matrix are doomed. The adjacency matrix is too noisy. It is the spectrum is perturbed by the presence of high degree nodes in this constant average degree regime. So you cannot hope to succeed by employing a spectral method based on the original adjacency matrix. However, the non-backtracking matrix is better behaved and there is hope. And so we have now a proof of this spectral redemption conjecture that I will tell you a bit about. Okay, so to state the main result we have on the spectrum of these non-backtracking matrices in the context of this stochastic block model, let me give the notation now. Here E of A is meant to be the block matrix I was writing. So E of A is the expected adjacency matrix, and if you recall the parameters of this stochastic block model, the spectrum of this E of A is going to be determined by a spectrum of a much smaller matrix, the matrix with entries B, sigma, sigma prime, alpha, sigma prime, with sigma, sigma prime being the potential categories that there are in your model. So you have this R-dimensional matrix, so you have potentially R eigenvalues that are non-zero, and then you have a lot of zero eigenvalues on top of that. And so mu's will be these eigenvalues of this matrix here. And then we need also the eigenvectors associated with these eigenvalues. So we are still looking at the expected adjacency matrix. So we are talking about an n times n matrix. So these are n-dimensional vectors. But since we want to talk about the non-backtracking matrix, we need to introduce vectors indexed by the oriented edges. So we just lift those eigenvectors x to eigenvectors y, where the entry associated with an edge E is just the entry of the corresponding x vector associated with the starting point of the edge. So this is one way to lift these node-indexed eigenvectors to edge-indexed candidate eigenvectors. So that's the first element of notation. Just as an illustration, in the symmetric two-community case that was the object of the Dessel et al. Conjecture, the mu's are the eigenvalues of this 2x2 matrix, and so you find mu1 is the expected degree of this random graph. So with my two parameters a and b, this is a plus b over 2. Mu2 is the other eigenvalue of this matrix, and it's a minus b over 2. And then you can remark something which is not innocent, that the transition point tau in the Dessel et al. Conjecture is precisely the ratio of the square of the second eigenvalue to the first eigenvalue. Okay, so more assumptions. I'll just focus on the case where the expected degree of nodes per community is the same in each community. And this is to make the problem of a community detection with positive overlap non-trivial. Otherwise, if you have distinct average degrees, you could just threshold the degrees, and you would achieve a positively correlated reconstruction. So the problem becomes interesting under this assumption. So now I'll distinguish eigenvalues mu according to whether they are above the square root of mu1 or not, and I'll call them visible if they are above the square root of mu1 and invisible otherwise. And so I'll let R0 denote the index of the smallest visible eigenvalue. So if R0 is 1, then there is no visible eigenvalue except the first one, mu1. If R0 is larger than 1, then we have some visible eigenvalues mu I for I larger than 1. And in that context, you can state this Keston-Stigum condition, which is the following. The parameters will satisfy this Keston-Stigum condition if there is a visible eigenvalue that is not the largest eigenvalue. So if there is an I larger than 1, such that mu I in modulus is strictly larger than the square root of mu1. So in particular, this Keston-Stigum condition in the two symmetric communities case is precisely the condition that the order parameter tau is above 1. So that's the situation where you have hope to do a positively correlated reconstruction. All right, so with all this in place, here's the result. First, the eigenvalues. So we have a stochastic block model with fixed community number R. We let n go to infinity. Then we don't assume necessarily the Keston-Stigum condition. This applies even without this. So for each mu I that was visible in the parameters of the model, then we have an eigenvalue lambda I of B, which is close to mu I with high probability. So the visible part of the spectrum defined through these mu's survives in B somehow. And for all the eigenvalues mu I, and these are the, okay, all the visible eigenvalues mu I give rise to one visible eigenvalue lambda I in B. And all the other eigenvalues of B are non-visible in the sense that their modulus is no more than square root of mu1 plus a little o of 1. So that's for the eigenvalues. And we also have a handle on the eigenvectors. So if we have a handle on eigenvectors for visible eigenvalues, and for visible eigenvalues that are simple, actually. So the characterization we have is as follows. It is not a deterministic direction that this eigenvector takes. It's a random direction that can be described as follows. So remember, y sub I is this lifted deterministic vector. So that would be the natural candidate eigenvector. It's not the correct one. You need to tweak it a bit. And the way you need to tweak it is by applying this B non-backtracking matrix k times transposed, and then k times again non-transposed for some sufficiently large k. And here sufficiently large means logarithmic in the number of nodes. So it's not deterministic, it's random, but it reflects some feature of the model parameters through the vector y. Okay, so that's the result, and it has as a first corollary a proof of the spectral redemption conjecture. So this goes as follows. So that's not just in the two community case. This is more general than that. So the assumption is that the Keston-Stigum condition is met. So we have one visible eigenvalue that is not the leading eigenvalue. We have equal community sizes, and we assume that the visible eigenvalue has multiplicity 1 to leverage our understanding of the eigenvectors in that case. And so under these conditions, here's a way of producing an estimation of the hidden labels that will be positively correlated. We first extract the corresponding eigenvector of B. We threshold its coordinates. So we cook up signs for all the oriented edges. Then for each node, we assign a sign that is, so here's a node U, it has outgoing edges like that. We pick at random one of these outgoing edges and we tag U with the sign we assigned to the edge. Okay, so we go back to nodes now, from edges to nodes. And finally, depending on this sign, we sample at random community type with a distribution that depends on the sign. So, okay, that's the canvas of the procedure. And we can prove, because of our characterization of the spectrum of B, that this will achieve positive correlation under these assumptions. So that's an illustration. So this is the spectrum of a B matrix for a 2-community stochastic block model. And here you have the Perron-Frobenius eigenvalue of this B matrix. Here you have in the complex plane the circle with radius square root of this Perron-Frobenius eigenvalue. And here you have this second eigenvalue that is visible, that is outside of this circle. And the corresponding eigenvector is the one we use to do a positive correlated community detection. So second corollary, so now we don't assume the Kesten-Stigum hypothesis, and we actually assume we have an Erdos-Renyi graph. So we have simplest possible case. So average degree alpha per node, fixed alpha. Then the way the theorem is applied here is to say that apart from the Perron-Frobenius eigenvector of B, all the other eigenvalues, sorry, so that's lambda 1, the Perron-Frobenius eigenvalue, all the other eigenvalues have modulus strictly less than or equal square root of lambda 1 plus little o of 1. So in other words, we have, apart from the little o of 1 correction, we have exactly this version of the Ramanujan graph property that I alluded to, defined in terms of the non-backtracking matrix. So in this sense, this corollary 2 is a version of Friedman's theorem for Erdos-Renyi graphs. If we accept as a definition of a Ramanujan graph that given in terms of the spectrum of B.
Sorry, probably your definition is so there's some. So this definition somehow incorporates the small components, right? But why small components? Why small components don't
what small components? Sorry.
They're
disconnected components.
So if they are tree-like, there would be a nilpotent term for the B matrix. So that will create 0 eigenvalues.
And the definition is such that. But they each contribute its own.
So for each eigenvalue, so that could be complex. Either its modulus is equal to that of lambda 1, or it's less than or equal to square root of lambda 1. And by the Ihara-Bass formula, we know that in the regular case, at least, this is equivalent to the classical definition of a Ramanujan graph. So if you have a disconnected component that is tree-like, it induces some 0 eigenvalues for B. Even though on the adjacency matrix it induces some positive real eigenvalues, this induces some zeros for B. All right, so that's the plot for the Erdos-Renyi case. So let me now say a few words about the proof. So the first thing is to write b raised to some logarithmic power as a sum of a low rank part, which is the one that you hope will capture the spectral structure, plus some perturbation term. So here the V's would be the candidate eigenvectors, so the Y's multiplied by B transpose to the K, B to the K. W would be a candidate for the left eigenvectors, so they are not the same because the matrix is not symmetric. The lambda i's would be candidate for the eigenvalues. And R would be a perturbation. If it was small, then it would be done. But we have to show it is small and to show that this small perturbation does not mess up too much the spectral structure of that, so that we can read off the spectral structure of this low-rank term, the spectral structure of B. So in order to do that, we need to show that the candidate eigenvectors are near orthogonal, same for the left ones and the right ones, that if you take two distinct indices, they are near orthogonal between the left and the right. We need to show that there is a low condition number for this low rank matrix. So that is to say the left and right eigenvectors are not orthogonal. They are sufficiently close by. And finally, we need to show that the perturbation matrix is small enough. And small enough is expressed in terms of the magnitude of the Perron-Frobenius eigenvalue here, mu1. And if you have all that, then you can leverage a tool from linear algebra, which is the Bauer-Feig theorem, which tells you having a diagonalizable matrix and with a good condition number, what is the impact of an additive perturbation on the spectrum? And Bauer-Feig theorem will give us our result here. So I won't state that unless you really ask for it. But, okay, so then the proof breaks down into two parts. There is a first part which I call a local analysis. So for instance, all the properties that the candidate eigenvectors form a near orthonormal system and that they have a good condition number follow from such a local analysis. And this local analysis involves looking at the local statistics of the random graph. And we know that this is close to a Galton-Watson branching tree. We can couple actually the neighborhood of the graph with such a Galton-Watson branching tree, and we can do all sorts of precise analyses on these. And so more precisely, for instance, if I focus on the scenario with two symmetric communities, spins -1 and +1, I have two candidate eigenvectors that I might care about. Let's consider, for instance, the right eigenvectors, which were these, you multiply some deterministic vector by b raised to the k. Well, the entries of those vectors would correspond, for instance, entry u would correspond to summing all the spins at distance k from u. So for the first vector, it would be counting the size of the neighborhood. For the second vector, it would be counting the weighted sum of this neighborhood weighted by the spins. And so we know how to do those things on the Galton-Watson trees. We can control this. We can do martingale analysis. We can control the fluctuations. We can do all these things. So this is involved in the proof. Another thing which is involved in the proof is since we have some martingale convergence theorems underneath, if we say look at the size of let's say the sum of spins at depth t, we know that this is, so that's the d term here, we know that this is going to behave like the weighted sums, the sum of the spins at another depth times some mu2 at an adequate power. And then there's a perturbation term which corresponds to fluctuations in the magnitude of the neighborhoods. And so these are central limit theorem-like fluctuations. So if we go to depth t, the size of the neighborhood would be mu1 to the t, hence the fluctuations would be order square root of mu1 to the t, whereas the quantities of interest for, say, the second eigenvector would be growing exponentially fast, like mu2 to the t. And this is where the Kestenstiegum condition appears. We get a good handle on this if this mu2 to the t is sufficiently large compared to mu1 to the t over 2. So that's precisely the Kestenstiegum condition. And the more difficult part, perhaps, in this proof is controlling the magnitude of the fluctuation. So to do that, we need, in fact, to prove that the norm of b raised to the k in the orthogonal of candidate eigenvector is small. And the difficulty is that b is random and the candidate eigenvectors are random as well. So we have correlated randomness here. So we have a difficulty here. And one trick that makes things work is to introduce this somehow centered version of b raised to the k. So this delta matrix with some exponent m would correspond to summing over paths of length m, a product of terms which correspond to the entry of the adjacency matrix minus some centering. And this is an auxiliary in our proof that is absolutely critical. So, and we need to control the path with sum over. So the natural thing to do would be considering non-backtracking paths. In fact, we need to also restrict ourselves to paths with a further tangle freeness property that I won't define. But once you have this auxiliary, you can expand the products here, and you get a matrix expansion involving terms which look like this delta matrix to some smaller power, and B matrix raised to a complementary power, the sum of the two powers being m up to some constant. So this is what we want to work on for now. So I'm rushing that, I know, but okay. So we have this expression. So showing that the delta terms are small is done using a classical technique in random matrix theory, which is due, I guess, to Furedian-Cohn laws. You can bound the you can bound the trace of the matrix raised to some power, and you can take expectations of that. This boils down to a combinatorial argument. So that is using the classical technique of Furedian-Cohn laws. The other terms in this expansion are harder, in a sense. To show that they are small, we do use the fact that we are considering vectors x orthogonal to the candidate eigenvectors. And these are random directions, but random directions determined by B. And we consider a scalar product of those vectors orthogonal to candidate eigenvectors with vectors that actually will be close to these candidate eigenvectors. And their closeness to the candidate eigenvectors will stem from this quasi-deterministic growth property that resulted from the local analysis. So, okay, so I'm not detailing any further. So, to conclude, there are many more interesting questions that one might want to answer on these stochastic block models. So here's one. So what I described tells you that under the Kestenstiegum condition, which is quite easy to identify, you just look at the spectrum of the matrix induced by your model parameters. So you check that there is a secondary eigenvalue whose square is larger than a leading eigenvalue. So we know that this non-backtracking matrix-based spectral method will achieve positive correlation. And in the two communities case, we knew also that either you could succeed in this way or nothing could succeed if you were below the transition point. Now, if you move to more than two communities, you have this phase above the Kesten-Stigum threshold where you know you can succeed. You have a phase where you know you will fail and any method will fail. And there is, for 5 communities or more, an intermediate phase where you know you're not under the Kesten-Stigum conditions, so the non-backtracking matrix method will fail. You know there is some signal in your observation, but you don't know how to catch it. So brute force maximum likelihood would achieve something, but a polynomial time method for extracting some correlations is not known, and that is conjectured to be quite hard. Another open problem that has been around for a long time now is the planted clique detection problem. So it's not exactly in the same setup, but close by. So you take an Erdos-Renyi graph with a edge probability presence 1/2, and you plant a clique of size k in here. So if the planted clique has size larger than square root n, any naive method will succeed in detecting the clique. Whereas if the clique has size small compared to square root n, no known polynomial time method can detect it. So it's been so hard and it has resisted so many attempts that now people use the planted clique detection problem as a benchmark for hardness. So they reduce their problem to detecting a planted clique in this model whose size is smaller than square root n, and say, oh, this is planted clique hard, so I can do other things now. All right, so that's it. So I think this is an interesting domain where there are still many exciting things to do, and this detection in the stochastic block model is, I think, a rich playground for looking at computational complexity issues with the lenses of probability theory and statistical physics. With this, I'll stop.
So I have 2 questions. One is, what is known on the, let's say, non-interesting part of the spectrum, so of the backtracking matrix, the one which is in the, let's say, in the circle? Is it characterized in the limit of?
I think that Florent Zakala and co-authors have tried to characterize the density in this circle. I'm not sure. Mark would know that. I think they were working on it, definitely. No, you don't? Is it known how the spectrum behaves in the circle? So I'm sure Florent was working on that, trying to characterize the density inside this circle. I don't know if he's completed this work, but he's been looking at it.
And the other question is, people have tried to detect community, I don't know, for example, for when you have data of, I don't know, for example, financial data, you have the evolution of different stocks. So they use the correlation matrix and they do something similar, meaning that they compare the spectrum of the correlation matrix to the Wishart, and all the things that pops out from the Wishart are considered a signal. And in this way, they detect the financial sector, for example. Do you know if there is something, this idea of the backtracking matrix can be generalized in some way into this case? So maybe the correlation matrix is not the best matrix to look at to identify sectors from data.
I think the correlation matrix, you can really relate somehow to the adjacency matrix of a bipartite graph. So there would be a very close correspondence between looking at the correlation matrix and the adjacency matrix, I would think. So that if that is true, that would suggest that you can indeed cook up a non-backtracking matrix in that context as well. And the advantage might be to reduce the noise in the data. So that's what it does for free. It reduces the effect, say, of high degree nodes in our models without any explicit pre-processing like trimming node degrees or that kind of things. So it might also have some benefits in that context.
Okay, thank you. More questions? Okay, I have a question. So in the regime when you said detection is infeasible, what does that mean precisely?
We have a number of negative results for the two community case. So one of them, for instance, is that positively correlated reconstruction in the graph is at least as hard as positively correlated reconstruction in a tree model, where you have a random tree. You have a probabilistic propagation of the spin sign from the root node down to the leaves of the tree. And so if you cannot infer with non-vanishing accuracy the spin at the root from the observed spins at the leaves, then in the tree model, then you cannot do positively correlated reconstruction in the graph model. And it is known in the two community case that below the Kesten-Stigum threshold, the tree problem is infeasible. So the best reconstruction you can do of a spin at the root of the tree from the spins at the leaves is as good as random noise as the tree depth increases. So that's one negative result. And there's another one, which is to show that your random graph observation below the threshold is contiguous to the random graph according to the Erdos-Renyi distribution with the same average node degree. So it seems to be a very strong thing, this contiguity result. However, you cannot deduce the impossibility of correlation, positively correlated reconstruction from it somehow. This is
So in the Erdos-Renyi model, what is the distribution of lambda 1?
Sorry,
what is the distribution of lambda 1? Doesn't it tend to infinity? As
no,
if you fix alpha, I mean, if you fix density alpha over n, if you fix the average degree and you let the number of vertices grow?
I think it would be the alpha, but that's a guess. So is there a proof of that? I think, yeah, we have this. We have this from the, yeah. So we have this from the theorem, actually. This corresponds to the mu1. So indeed, this would be alpha, the average degree. Yeah.
Okay, let's thank the speaker again, and let's reconvene in 20 minutes.